I'm sharing my screen. So last class we seen about this asynchronous counter 2-bit, no? So this class will discuss about the asynchronous counter design of asynchronous counter 3-bit.
GLS means, yeah, GLS is first verification environment is there. To make GLS environment, we have to do like this.
One second.
These all things.
One second. Yes. So here, so you need to design this asynchronous counter. So there are some steps are there. So I will design the asynchronous 3-bit counter, 3-bit counter. So asynchronous, there are two types of counters. Last class I told you like asynchronous counter means the output of one flip-flop is acting as a clock for the next flip-flop. Okay, synchronous clock counter means common clock is given to all the flip-flops. So today we'll discuss about how to design this 3-bit asynchronous counter. Okay, 3-bit asynchronous counter. So basically the steps are there. So you need to follow this step. Okay, step one. Okay, so step one. So what is this step one means? Step one, select the type and number of flip-flops needed. Okay, select the select the type and number of flip-flops needed. Number of flip-flops needed. Okay. You need to, so basically last class I told you, you are using JK flip-flop and T flip-flop. You can design by using D flip-flop also. Okay, so this should be operated in which mode? Toggle mode. Toggle mode means what? Where J equal to K equal to 1 and T should be equal to what? 1. Okay, and all the flip-flops will be toggle mode that I told you, no? So this should be operated in which mode? Toggle mode. Okay, so all the flip-flops should operate in toggle mode. Okay, in toggle mode. Okay, toggle mode means what? When j equal to k equal to 1, qn plus 1 equal to what? Qn bar. Okay, similarly t equal to 1 means qn plus 1 equal to qn bar. Okay, and step 3, direct clock is applied to lsb of the flip flop. So we already seen in the last class, that is direct clock is applied to LSB of the flip-flop. Okay, LSB of flip-flop. Okay, and first flip-flop is applied as a clock to the second flip-flop. Okay, so that means common clock is not there. First flip-flop. So the output of first flip-flop output, first flip-flop output is applied as a clock to the next flip-flop. As a clock to next flip-flop. Okay, so these are the steps you need to follow. Okay, so this is asynchronous counter. First, I will design this asynchronous up counter. How will I design asynchronous up counter? Okay, so here first I'm choosing first step. I'm choosing T flip-flop. Okay, I'm choosing T flip-flop. Okay, so T flip-flop means I'm using 3-bit asynchronous up counter. So asynchronous up counter. So if it is asynchronous up counter, so for n-bit counter, you have n flip-flops. So here also you need 3 flip-flops. Okay. How to find out mod of this counter? So that means there is a formula, n is less than or equal to 2 power n. Okay. So that means n is less than or equal to 2 cube. So this is nothing but a mod 8 counter. Mod 8 counter. Okay, this is mod 8 counter. Okay, so here so I'm drawing this, so I'm designing asynchronous up counter. Okay, that is 3-bit asynchronous up counter. Okay, here I'm designing asynchronous asynchronous up counter, that is what 3-bit. Okay, 3-bit asynchronous up counter. Okay, so I'm using how many flip-flops? 3 flip-flops, no? So let us take this is T naught, T naught flip-flop, and T1 flip-flop, and T2 flip-flop. Okay, T2 flip-flop. So here this is T naught, Q naught, T1, Q1, and T2, Q2. Okay, so here so these all the T inputs are operated in which mode? Toggle mode. Okay, all the T inputs are operated in toggle mode. So we already seen the truth table for T flip-flop. So when T equal to 0, it will be in the memory state. When T equal to 1, it will be in the toggle state. Okay, so that is I'm giving to logic 1. Okay, and I'm using negage of clock. I'm using negage of clock. Okay, so this is T flip-flop. Okay, flip-flop, you can write this is flip-flop 0, flip-flop 1, and flip-flop 2. Okay, so here if I am using negage of clock, what I need to do, this q is acting as a clock to the next flip flop. Q is acting as a clock to the next flip flop. Okay, and here also q1 is acting as a negage of clock to the next flip flop. Okay, and here so that means you are taking the outputs from where. So this is MSB of the flip flop. Rightmost bit is MSB of the flip flop, and leftmost bit is nothing but LSB of the flip flop. Always leftmost bit is will toggle. Okay, always leftmost bit will toggle. Okay, so this one you are taking out, and q naught you are taking out, okay, so this is nothing but my counter output. So this is q2, q1, and q naught. Okay, q2, q1, and q naught. Okay, so first, so here I will write the counts. Okay, and I will analyze this one. Okay, so that means first, uh, so clock, and q2. Q2 is nothing but MSB of the flip flop. Next q1, and q naught. Q naught is nothing but LSB of the flip flop. Okay, so initially I am giving what I am giving the clock as 0. So when I am giving clock as 0, initially all the flip flops will be what? So here I am rubbing this. This is LSB of the flip flop and MSB of the flip flop. Okay. So here, so this will, be 0 only. So initially the output of flip flop will be initialized to 0 only. Okay. So output of flip flop will be initialized to 0. Okay. And next, so next what I am giving. So all the flip flops will be 0 only. Okay, so and next, if I'm applying first clock pulse. Okay, if I'm applying first clock pulse, what happens, so always this will toggle. Okay, first clock pulse, so 0 clock pulse means what? All are 0 only. First clock pulse I am applying, this will toggle, so this becomes 1, and remaining all are what? So that means 0 to 1. 0 to 1 means passage of clock. So but this will toggle when you are getting negage of clock, but here there is a passage of clock. Okay, so this will be in the previous state only, so 0 and 0 0, there is no toggling. Okay, there is no triggering is happening, so that means it will be 0 only. Okay, so that means when clock equal to 1, it will be what? 0 0 1. Okay, 0 0 1. And at second clock pulse what happens, so this will always toggle, so this becomes 0. So it is changing from 1 to 0. So this is negage of clock. So negage of clock means this will trigger. Okay. So this will trigger. This becomes what? 1. Okay. 0 to 1. This is passage of clock. Passage of clock means what? This will not trigger. It will be in the same state, previous state, 0. Okay. So that means here you are getting 0, 1, 0. Okay. And at third clock pulse, we'll see. At third clock pulse, always this will toggle. Okay, so this is 1 and this becomes 1, and this is 0 to 1 means what? Passage of clock. Passage of clock means what? Passage of clock means so this will be in the same state. Okay, so it will trigger when it is negage of clock. Okay, so this will be in the same state, and there is no triggering, so this will be in the previous state is 0 only. Okay, so that means at 3 you are getting 0 1 1. Okay, 0 1 1. And next, at 4. Okay, at fourth clock pulse what happens, this will trigger from 1 to 0. So 1 to 0, so 1 to 0 means negage of clock, so that means this will trigger. Okay, this will trigger from where to where? 1 to 0. Okay, so 120 means negate of clock. Negate of clock means this will trigger. Okay, so this will toggle. Okay, this will toggle and it becomes what, 1. Okay, so in this case you are getting at fourth clock pulse 100. At fourth clock pulse you will get 100. Okay, and next next what you are getting, next you see at fifth clock pulse. At fifth clock pulse. So this will toggle from 0 to 1. This is passage of clock. So this will be in the same state. This is 0 and there is no triggering. It will be in the same state only. Okay, this will be 1 only. Okay, at fifth clock pulse, what happens? You are getting 101. Okay, at fifth clock pulse, you are getting 101. Okay, at seventh clock pulse, we'll see. Okay, seventh clock pulse. At seventh clock pulse. Yes, yeah, it is a seventh clock pulse. We'll see at the seventh clock pulse. At seventh clock, sorry, at sixth clock pulse, what happens? This will toggle from 1 to 0. 1 to 0 means what? Negate of clock. So this is negate of clock means this will toggle. Okay, this becomes what, 1. 0 to 1 means what? Passage of clock. So it will be in the same state. So it will be in the same state means 1. Okay. At sixth clock pulse, what happens? You are getting 110. Okay. And next at seventh clock pulse. Okay. At seventh clock pulse, what happens? At seventh clock pulse, yeah, at seventh clock pulse, we'll see the operation. So this will toggle from where to where, 0 to 1. 0 to 1 means what? Passage of clock. So passage of clock means what? This will not toggle. It will be in the previous state only. What is the previous state? 1 only. And 1 to 1 means there is no toggling happening. So that means it will be in the same state only. So that means the next state will be, this is 1 only. You are getting 1 only. Okay. At seventh clock pulse, it will come to 1 1 1. Okay. At eighth clock pulse, we'll see. At eighth clock pulse, what happens? This becomes 1 to, this will toggle from 1 to 0. So this is negate of clock. Okay, 1 to 0 negate of clock. So what happens? This will toggle. So this becomes what, 0. Okay, it will toggle from 1 to 0. So again, so this is negate of clock. This will toggle. So this will come from 1 to 0. So at eighth clock pulse, all the states becomes 0. All the states becomes 0. Okay. So if you draw the state diagram, what is the initial state? 0 0 0. Okay, this is the initial clock. And if you are applying first clock, it will go into next state 0 0 1. And second clock, it is going to the next state 0 1 0. Third clock, it is going to the next state 0 1 1. Fourth clock, it is going to the next state 1 0 0. Fifth clock, fifth clock, it is going to 101. And sixth clock, it is going to 110. Seventh clock, it is going to 111. And at eighth clock, it will come into the initial state. Okay, it is coming to the initial state. So based on this, so if what you observe, that means LSB of the flip-flop will always toggle. LSB of the flip-flop will always toggle. And next flip-flops toggling is depending on the output of this. This toggling is depending on the output of this Q0, and this toggling is depending on the output of Q1. Okay. So you can draw the timing diagram also. So for this, if I draw the timing diagram, so first I'll draw the clock. Okay. First I will draw the clock. So if I draw the clock, so total how many clock pulses are there? 8 clock pulses are there. Okay. So 8 clock pulses. So I'm drawing the clock. Okay. Yeah. Here I'm drawing the clock. Okay. Yeah. So here I'm drawing the clock. So this is a uh, 0 clock, first clock, second clock, okay, and third clock, fourth clock pulse, fifth clock pulse, sixth clock pulse, and seventh clock pulse. And next, this is eighth clock pulse, okay, eighth clock pulse like this, okay. So this is clock. This is what? Clock, okay. And this is what neg edge of clock, no? So neg edge of clock means what? During this neg edge, the output will change. During this neg edge only, the output will change. This is neg edge of clock. Okay. When it is transition from 1 to 0 only, the output will change. Okay. Neg edge of clock. Okay. So that means I told you. So if you see this diagram, always LSB of the flip-flop will always toggle. So that means Q naught will always toggle. Okay. Q naught will always toggle. Okay. So that means if you draw for Q naught, so if you draw for Q naught, so I'm drawing for Q naught. Okay. So this is so here I'm drawing for Q naught. So this is so neg edge of clock. So during this neg edge, so what happens first initially, this is for Q naught I am drawing. Okay, initially Q naught is what? 0. Okay, Q naught is 0. Okay, after that, during this neg edge, it becomes what? It becomes just I will change the color, blue color I will change. Okay, so this will change from where to where? So 0 to 1. 0 to 1. During this neg edge, again it will toggle from 1 to 0. Always at the at the neg edge of clock, it will toggle. Okay. Why? Because clock is directly applied to the LSB of the flip-flop. No? So that's why it will toggle. Okay. It will toggle like this. Okay. It will toggle. Okay. It will toggle like this. Okay. And next, this Q naught is acting as a clock to the Q1. Okay. So that means this is neg edge of clock. This is neg edge of clock. Okay, so Q naught is acting as a clock for Q1. So if you draw for Q1, if you draw for Q1, so that means initially this is 0 only. This is 0 only. So here it will toggle from where to where? 0 to 1. It will be 1 till next neg edge, and next after this it will toggle to 0, and next neg edge it will toggle to 1. It will toggle to 1. Again it will toggle to 0. Okay, so this is Q1. Okay, and next this Q1 is acting as a clock for what? Q2, neg edge of clock. Okay, this Q1 is acting as a clock to Q2. Okay, so here if you draw the for Q2 timing diagram for Q2, so what you are getting? So initially Q2 is 0 only. Okay, so Q2 is 0 only. Okay, initially Q2 is 0 only. So till next neg edge it will be 0 only. Next neg edge, it will be 0 only. So during this neg edge, it will toggle from 0 to 1. Okay, 0 to 1. And during this neg edge, again it will toggle from where to where? Again it will toggle from 1 to 0. 1 to 0. Okay, so 1 to 0. So like that it will repeat. Okay, it will repeat. So from here, if you draw, so if you write, so this is MSB of the flip-flop. Q2 is nothing but MSB of the flip-flop, and Q1 is nothing but LSB of the flip-flop. Okay, so here if you write, this is what? 0 0 0 0 0 0, and next 0 0 1, and next 0 1 0. Okay, next 0 1 1. Okay, and next 1 0 0. Okay, and next 1 0 1. Okay, next 1 1 0, and 1 1 1. Again it will coming to initial state 0 0 0. Okay, so like this. So that means this is nothing but what? This is 0, and this is 1 2 3 4 5 6 7. Again it is coming to initial state 0. Okay, so like this it is acting as a up counter. Okay, asynchronous up counter. Hope you understood. So this is asynchronous up counter. Suppose if I want to design asynchronous down counter, what I need to do? So what I need to do? So I need to connect. So that means this is neg edge of clock. Q naught bar. I need to connect as a clock to next flip flop. This you can analyze. Okay, this you can analyze with your own. So I told you up counter, no, so that you can analyze with the Q1 bar. So this is acting as a clock to the next flip flop. Okay, this is acting as a clock to the next flip flop. So summary, what I can say, suppose, so in conclusion, what I can say means, if it is negage of clock. Okay, negage of clock. Okay, if it is negage of clock, so um, if it is, I want to design the up counter. Uh, so if I want to design up counter, Q naught and Q1, okay, is acting as a clock to next flip flop, okay. If it is down counter, what I need to do? I need to connect the complement, that is Q naught bar and Q1 bar as a clock to the next flip flop, okay. And passage of clock also you can analyze, okay. So if it is passage of clock, so what is the conclusion? If it is up counter, so Q naught bar, Q1 bar will be act as clock to the next flip flop, okay. And if it is down counter, so Q naught, Q1 should act as a clock to the next flip flop, okay. So that means you need to come from the basics. Suppose if you understand the operation of 2-bit counter, 2-bit asynchronous counter, yesterday I explained. Okay, yesterday I explained the 2-bit asynchronous counter. You can understand 3-bit asynchronous counter easily. Okay, so 2-bit asynchronous counter I explained yesterday about this operation. Up counter and down counter also I explained. Okay, and here so this is 3-bit up counter. Okay, so depending on the this one asynchronous or ripple counter, the output of one flip flop is acting as a clock to the next flip flop. Okay, so we'll go with the programming, how to write the program for this asynchronous 3-bit asynchronous up counter. I wrote the program. See here, asynchronous up counter 3-bit. Okay, asynchronous up counter 3-bit. Okay, so this is asynchronous up counter 3-bit. So if you see this, yeah, means in this, what I am doing means here I need to initialize the, so that means the module, okay, it will start with module and a module, one second, I'll expand this. Yeah. So this is a module asynchronous. So this is the identifier asynchronous up counter 3-bit. And how many inputs will be there? Input clock, input reset. Okay, input clock, input reset. And so this is a gauge of reset. Okay, asynchronous up counter 2-bit. Okay. So I can use the negate of so here I'll use asynchronous reset underscore n, and here I'm using so based on my like negate of reset. Okay, based on my design only I wrote. Okay, negate of reset, negate of clock, and here I'm using asynchronous active low reset. Okay, negate of reset only. Okay, negate of reset. Okay, always at the right negate of reset. Okay, one second. Negate of clock and negate of reset underscore n, no? Okay. Reset underscore n. Okay. So negate of clock and negate of reset. Okay. So here you see, if reset of n, reset underscore n. Okay. This is the nomenclature for negate of reset. Input clock and input reset underscore n, and I'm using a vector. Okay, 2 down to 0. So how many outputs are there? 3 outputs are there, no? 2 down to 0. So that means Q0, Q1, Q2. Okay, these are the outputs. And I'm initializing one more that reg with 2 down to 0, ridge underscore Q. Okay, ridge underscore Q. Okay, and so why I'm declaring means here I'm operating with this. Okay, at last I am assigning this q underscore reg with this q. Okay, so always at the rate negate of clock or negate of reset begin if reset of so if reset equal to 0, I'm initializing the output of count to 0, else q underscore reg equal to
Sorry,
what?
not of reset, right?
One second. Yes, sorry. This is asynchronous active low reset, no, not off reset. Yes. If it is passage of reset means reset equal to 1. Okay. Not off reset means I am clearing this. I change to asynchronous reset, no? Okay. So 0, 0, 0, and I'm incrementing the count end, and I'm assigning the value q equal to q underscore reset. I'm using continuous assignment statement and end module. Okay. And coming to the test bench, asynchronous, this is 3-bit. Okay, asynchronous 3-bit. Whatever the inputs are there that I need to initialize with reg data type. Okay, one second. Somebody has joined. One second. Yes. Okay. So here, so whatever the input variables are there that I need to, so module and TB underscore synchronous counter underscore 3-bit reg, whatever the inputs are there that I need to initialize with clock. Okay, only 5 steps are there for test bench, and whatever the outputs are there that I need to initialize with wire data type, and I'm using a vector 2 down to 0q integer I, and I need to instantiate. Okay, I need to instantiate that is then synchronous. So my what is my instance name? What is my asynchronous? No, one second. Asynchronous. This is synchronous. One second. This is synchronous. Asynchronous account. Synchronous. Asynchronous. This one. Okay, this one. I need to set a stop. I need to set a stop. This one. Okay. So asynchronous up counter 3-bit unit under test, and clock reset Q. Okay. So clock reset and Q. Okay. These are the variables outside. These are the design inputs, and these are the test bench inputs. And I need to generate the clock initial begin clock equal to 0, and I'm giving reset. Okay. Whatever the reg variables are there. I need to initialize, and I'm so here I need to keep reset equal to 0. No, I need to make reset reset equal to reset equal to 0, and one second. These are nothing but reset underscore n, and this is reset underscore n, reset underscore n, and reset underscore n. Okay. First I am making reset underscore n equal to what? 0, and after that reset underscore n equal to 1 I am making. Okay. Why I'm getting mm, reset underscore n. Here also reset underscore n. Okay. I think now it will go. Okay. First I'm resetting to 0. So this is asynchronous active low reset. After 5 minutes, I'm making this. This is nothing but reset mode, and making this reset mode to functional mode. Okay. So I'm making after 5 minutes, I'm making this into functional mode. Okay. And next what I'm doing. Yes. One second. Hmm. Yeah. So next what I'm doing. Yeah. So next I need to generate the clock, no? So I generate the clock. Okay, clock equal to not off clock. Okay, I generated the clock. Okay, for I equal to 0. For I'm using for loop. Okay, why? Because 16 pause all the combinations I need to check. Okay, and for the 5 minutes I'm toggling the clock, and I'm displaying these values, and I'm finishing the simulation. Okay, just I want to see this. So run simulation, run behavioral simulation, and save this. I'm getting errors. Okay, where I'm getting errors. Visual console. Mm, Yeah, where I'm getting error, I need to see. Okay.
Sir, I think in dollar display you should write RST/n reset/n.
Dollar display. Okay, this one. Okay, 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 okay. Thank you. Okay, reset. I change the variable, no? Okay, okay. So just I'm facing difficulty. Please help me. Okay. Yeah, yeah. So I got the waveform. So I think I can see the output in TCL console also, no? So TCL console, I'm getting this one. See here. So when clock equal to this is a 1 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. After that again it is resetting to this 0. So it is acting as up counter only. Okay, it is acting as up counter. Okay, and you can see in the simulation part also. So just expand this and fit to page, and these are the so here when reset equal to 0, okay, this is nothing but reset equal to 0. This is nothing but reset mode. Okay, so when it is going from reset mode to functional mode, so what happening immediately the output is not changing. When it is changing during the neg edge of clock, it is changing. Okay, so that means reset to means reset mode to functional mode is synchronous. Okay, synchronous with the clock, that I told you, no? So that means reset removal is synchronous, but reset applied is asynchronous. Okay, asynchronous irrespective of clock and inputs, immediately it will reset the circuit. Okay, here I didn't done in the test bench. You can analyze that. Okay, so during the neg edge of clock, so what happens, the counter is incrementing. So during the negage of clock, the counter is incrementing. Okay. Yeah. So during this, so it is up counter. Okay. 0, 1, 0 to 7. And after that, 0 to 7. Like that, it is good doing up counter. Suppose if you want to design a down counter, what I need to do? So in the design itself, I need to keep which one, asynchronous 3-bit counter, no? So which one? Asynchronous. This is asynchronous 3-bit counter. So if I keep, I can give one also. I can use one tick binary one also. Okay, anything it will take. Okay, so just this is down counter. Okay, so I can give the down counter. I can change. So I'm checking whether my design is acting as a down counter or not. Okay, um, so uh, so run the simulation, run behavioral simulation, the behavioral simulation. So I can see the outputs in the TCL console also. See here, either it is acting as a, it will start from 0, okay, and it will start from the 111, 110, 101, 100, 011, 010, 001, and 000. Okay, and after that again it is starting. Okay, these inputs only I can see in the simulation waveform. Okay, so just here elaborate the design and fit to page. So initially when reset is 0, the output is 0 only. Okay, the output is 0 only. So when it is going from reset mode to functional mode, during the neg edge of clock only the output is changing. Okay, it will start from where high means down counter. No, it will start from 7, 6, 5, 4, 3, 2, 1. Okay, during the neg edge of clock only the flop will trigger. Okay, so that's why because in always block in the sensitivity list you given like neg edge of clock and neg edge of reset, no? So that based on that it during this neg edge of clock only the output will trigger, and you are getting this I can use as a down counter. Okay, this is nothing but down counter. Okay,
Sir,
yes.
what logic actually will change to get the down counter? Can you show the design once again, please?
Yeah, you want means in the program itself I changed here like
Okay,
asynchronous.
-1. Okay,
Yeah,
okay, okay.
only this
Design.
one, this
Yeah,
one.
okay.
Here I can keep one tick binary one also, or one also you can, it will take. So
Okay,
previously if it is up counter means I given plus. If it is down counter means I given minus. That's it.
okay, understood.
Understood? Okay. Yeah. Is there any doubts or queries based on this asynchronous
The
3-bit
modulus
counter?
of means actually what? Can you once again? explain, sir.
Yeah, mod of the counter, modulus of the counter means suppose like 1 second. So here, if you see, suppose, yeah, mod of the counter means counter, suppose mm, counter is having mod, if it is mod and counter. Okay. So mod and counter means from where to where it will count means from 0 to n minus 1 it will count. Okay. So first we already seen mod 4 counter. Okay. Mod 4 counter means 1 second. Mod 4 counter means so mod 4 counter we already seen. Mod 4 counter means it will count from where to where 0 to 3. 0 to 3. Okay. And today we already seen mod 8 counter. So mod 8 counter means it will count from 0 to 7. Okay. Suppose if it is mod 16 counter. So mod 16 counter means it will count from where to where 0 to 15. Okay. Suppose like you want to design a decade counter. Decade counter. So decade counter means what? It will count from where to where. So that decade counter means so you can understand this. This is nothing but mod 10 counter. Why? Because decade counter means it will count from 0 to 9, and after that it will come to where 0. Okay. So from this I can understand this. This is mod 10 counter. Okay. So means I need to decide the number of flip-flops required to design this mod 10 counter. Okay. So I need to apply the formula. This is nothing but n is less than or equal to 2 power n. Okay. So this is the formula to find out the number of flip-flops. Okay. Here if you apply suppose 10 is less than or equal to 2 power n. Suppose n you are keeping as 3, 10 is less than or equal to 8. Okay. Is this statement is correct or wrong? The statement is wrong. Why? Because the 10 is not less than or equal to 8. Okay. So this statement, so that means 3 flip-flops are not required to design this mod 10 counter. So next I will keep n equal to what? 4. Okay. N equal to 4 means what? 10 is less than or equal to 2 power 4. So 10 is less than or equal to 2, this is 16. This is nothing but 16. Now this condition is satisfying. 10 is less than or equal to 16 means what? How many minimum number of flip-flops required to design mod 10 counter or decade counter? I require 4 flip-flops. Like this you can decide. Suppose number of flip-flops are not given. Okay, you need to find out like this. Suppose mod 7 counter is there. So mod 7 counter you need to design. Okay, so mod 7 counter means what? N is less than or equal to 2 power n. Suppose if you are keeping n equal to 2. Okay, so 7 is less than or equal to 2 square. So 7 is less than or equal to 4. This condition is false. Next you need to keep what? 3. Okay. So 7 is less than or equal to 2 cube. 7 is less than or equal to 8. So this condition is satisfying. So how many minimum number of flip-flops are required to design mod 7 counter? 3 flip-flops are required. Now you understood what is the purpose of mod?
Yes. Yes, I understood. Thank
Okay.
you, sir.
Yeah. Anyone have any doubts or queries? Yeah.